All right, so we have air, which is assumed to behave as an ideal gas with constant specific heats. Oh, and it's in English units, unfortunately, but that's okay. So let's go ahead and draw things. So I have air. Oops. Got air coming in. It is coming in T1, 340 degrees Fahrenheit. And I might as well just go ahead and put this in degrees Rankine just in case that I need to. Might as well. And then let's see, it's coming in at E155 PSI, and then we're given a volumetric flow rate, V.1, of 5 feet cubed per minute. Okay, so it's coming in. Go. And just to kind of save space, I think what I'm going to do is I'll have it coming out right here. It doesn't really matter. But it's coming out at T2, 140 degrees Fahrenheit. And again, we might as well put it in degrees Rankine. And P2, 14.7 PSI. And let's see, I want to find, put it right here. So I want to find the work generated for the process in BTU per pound mass. So what I'm looking for little w. Then I want the rate of entropy produced. So I am looking for sigma dot. I know it's sigma dot, not sigma dot over m dot, because I have BTU per second degree Rankine, not BTU per pound mass degree Rankine. And then I also want to find the isentropic efficiency of my turbine and typical assumptions that I'm going to make for a turbine. And I'll get the ideal gas thing in a second. But typical assumptions that you're going to make for a turbine: steady state, dots equal to 0, changes in kinetic and potential energy are negligible. There we go. So that's good. And then they also told us that we got an ideal gas, and we're supposed to assume constant specific heats. And so what I'm going to do is I think that I'll probably need two things here. I think I need, well, before we get that, it's going to be taken at the average temperature, which in this case would be, so it's the average of 340 and 140. So 200 degrees Fahrenheit. Okay, so before we go forward, let's just go ahead and go to A20 and pull out the properties that we think we might need. There we go. Oh, actually A20E, right? So there we are. We were going to get there eventually. Yeah. So there we go. We got air, 240, which is right here, but yeah, so you can see if I want my CP, it's going to be between those two guys. And if I want my, yeah. All right. And so if I want the K value, I think on the answer sheet it looks like I had rounded it off, or it got rounded off on the spreadsheet. I don't, that's went into our calculations, but that's okay. No problem. So all right, so I realized that I had interpolated between 100 and 200, and I should have done between 240. So anyway, since fixed that, so we're going to need our CP value and our K value, and so I ended up getting a CP value of, let's see, 0.242 and a K value of 1.396. Now, as far as, why do I know that I need those two things. I do know I need them because, well, I've got an open system, so I know I'm going to have some delta H's, and I also have an ideal gas. I think I might be using some isentropic relationships, so going to get both of those guys. So I got a CP. CP is our 0.242 BTU per pound mass, degree Rankine, and our K value is 1.396. Perfect. All right. And again, you would kind of figure out that you need those as you went along. I just kind of know that I'm going to need them looking ahead. All right. So I'm going to do, anytime you get an open system, go ahead, and it's probably a safe bet that you're going to have to apply your conservation of mass, your conservation of energy. Maybe you're going to have to apply an entropy balance. And then if you've got an isentropic efficiency, probably going to have to write those things down as well, write that definition down. So let's go ahead and start. So my conservation of mass, well, one inlet, one outlet, not very exciting, but m dot is constant. And you know what I want to do? I want to actually put a little, oh, that's fine. Put a little W dot, or M dot times little w there. All right, so there's my conservation of mass. I also have my conservation of energy. So my conservation of energy of dETT equals Q dot minus W dot plus, I have stuff coming in, M dot times H plus kinetic energy plus potential energy, all coming in, minus, same thing, going out. And I'm going to go ahead and cancel out changes in kinetic and potential energy, the term related to whether or not steady state, right? The change in energy contained within that system boundary. Oops, get rid of you. And I don't have any heat transfer, and so all I should have left is the W dot, and it's equal to the sum of the M dot H's coming in minus the sum of the M dot H's going out, and the M dot is the same at the inlet as it is the outlet, so I'm going to be left with M dot times H1 minus H2. Perfect. All right, and then of course I know little w is going to be W dot divided by M dot. And that's H1 minus H2. And then, of course, because I know I've got an ideal gas with constant specific heats, I'm going to put that delta H in terms of Cp delta T, T1 minus T2. And I have T1, I have T2, I have the Cp now, and so it should be just a matter of plugging things in. I end up getting a little w of 48.36 BTU per pound mass. So 48.36 BTU per pound mass. Perfect. All right. So that's that guy. The next thing that we need to do is we need to apply our entropy balance. So our entropy balance for an open system, I have the rate of change of entropy contained within the system is equal to the rate of entropy transferred by heat transfer plus the net rate of entropy transferred by mass flow plus the rate of entropy produced. And of course, I don't have the DSDT term because it's steady state. There's no heat transfer, so there's no entropy transferred by heat transfer. And so all I should have left is sigma dot, and it's going to be m dot times S2 minus S1, or m dot times delta S. And I have very specific ways that I need to define delta S for an ideal gas, and even, for an ideal gas with constant specific heats. So let's go look. Let's see. So, all right. So we're right here. So we have ideal gases, actually, ideal gases, and here's our delta S if we assume specific heats to be constant. I've got two equations that I can use. Since I know the pressure ratio, that's probably the one that I'm going to use, and we use this guy right here. So, all right. So, oops. So my sigma dot is going to be equal to m dot times our delta S, which is the same thing as Cp natural log T2 over T1 minus R natural log P2 over P1. And let's go ahead and plug those numbers in so we don't get mixed up. Make sure we know what we're plugging in. So, and I don't actually have my mass flow rate, but that's okay. I have the volumetric flow rate at state 1. So let's actually bring him over here. There we go. So m dot, let's kind of put him in a different color so we know we're doing something a little different. So we need that mass flow rate. We've got the volumetric flow rate. So this is going to be V dot, and it's taken at state 1 over specific volume at state 1. And we have an ideal gas. So this is going to be V dot over RT over P. That R is our specific gas constant. So that specific gas constant is R bar over our molar mass. I'm going to bring that pressure up here, and there's our T1. So yeah, let's go ahead and plug those things in, make sure we got everything. So our molar mass for air, 28.97 pound mass per pound mole. Ooh, might be in trouble here with the amount of room I've given myself. My V dot, what was he? 5 feet cubed per minute. I've got my pressure 55. Oh, and I'm realizing on my, it's not in pound mass, it's pound force per inch squared. Okay. All right. Then I got an R bar on the bottom, so 1545 foot pound force per pound mole degree Rankine. T1 absolutely needs to be in degrees Rankine, so 800 degrees Rankine. And actually looking at it, I think I just have the feet and the inches to reconcile. So I've got 144 inches down here, inches squared, 1 foot squared down here. I think that should work out. So I've got a mass flow rate of 0.93, and it's going to be pound mass per minute. There's our m dot. All right, and of course, this guy also has to be R bar over my molar mass. Same thing that I did over here. Here's my molar mass. Here's our R bar, right? There we go. But I don't think, as long as you put, actually, yeah, let's make sure we've got the right units plugging in here. So I've got 0.93. This is pound mass per minute. And then that's all going to be multiplied by Cp, which we said was 0.242. So 0.242. And this is going to be BTU per pound mass degree Rankine. Natural log T2, and you need to put it in degrees Rankine. So 600 degrees Rankine over 800 degrees Rankine minus R bar over my molar mass. So in this case, because I want my units to work out right, I'm going to use the R bar that's got a BTU in it. So that's going to be a 1.986 BTU per pound mole degree Rankine. There we go. Oops. Oops. That's fine. Okay. We'll fix it. Divided by my molar mass, 28.97 pound mass per pound mole. Okay. Okay. That's minus. And then this is going to be times the natural log of P2 over P1. So I'm a P2 14.4 or 14.7. And it's PSI over PSI, doesn't really matter. And then 55. Okay. So plugging all that stuff in, get, I don't know what we get. Oh, there it is, 0.019, and that's going to be BTU per second, actually per minute degree Rankine. There we go. I don't know, they might have asked for it per second degree Rankine. Yeah, I guess in that case, we need to multiply or divide by 60, right? 1 minute divided by 60 seconds. And that would give us things in terms of BTU per second degree Rankine. All right, the very last thing that we're supposed to do is we're supposed to find the isentropic efficiency of this guy. So it's a turbine defined by work over isentropic work, which we know from our first law that the work is this guy right here, H1 minus H2, and we had put that in terms of CP delta T. So this guy on the top, I'll have a CP times T1 minus T2, CP times T1 minus T2S. Of course, those CPs are going to go away. I have the T1, I got the T2. Those are the things that were given to me, right? You could leave it, well, the 800 and the 600 degree Rankine, right? Yeah. So need to find T2S. And in order to do that, we're going to apply an isentropic relationship. And we're lucky because we have constant specific heat. So we're going to use one of the easy ones, one of these ones down there. All right, so I got T2S over T1 equals P2 over P1 to the K minus 1 over K. I've got the K as 1.396. Make sure that you plug those temperatures in as degrees Rankine, otherwise you're going to get a wrong answer. But I've got a T2S value of 550.29. There we go. And so if we plug that in, we end up getting isentropic efficiency of 80%. All right, hope that was helpful. Let me know if you have any questions.